Okay, yeah. So we're trying to do the posterior derivation for the case where mu is unknown and sigma is known. So as we had done it in the beta binomial case, remember we expressed the likelihood, we expressed the prior, and then tried to look at the posterior to see if we can recognize in some way. Okay, so in order to get there, of course, there are some algebra techniques that it's good to know. So I'm gonna do it giving some hint and let you do some practice. So first of all, let's work with the likelihood function. So the likelihood function, we know y1 to yn, they're IID. So given sigma and mu, they're IID normal mu sigma. Okay? And so now, the likelihood function, remember likelihood is always a function in terms of the unknown parameter. And because now mu is unknown, okay, so we express it as L mu. So what is L mu? So we know that they're IID. So it's going to be the product of each of the individual density. Okay, so let me write the PDF for you. So in the biggest parenthesis, it's the density PDF of each observation yi, the contribution. And then because they're IID, they're independent, so the joint will be the product of all of them. Okay. So I mentioned this to you earlier, that while we usually understand normal in terms of mean and standard deviation or variance, it will be easier for us to think about something we call precision. So let me just give you the definition again. Precision is 1 over sigma squared. So it's the reciprocal of the variance. So right now, we're going to work with this because it's easier for the derivation, and then we can see the results in a clearer way, right? So that means we're going to replace the sigma in the likelihood function with 1 over phi. So this means sigma squared is 1 over phi. All right, so I'm going to do that step for you, and then I ask you to try the next step. So now it's 1 over phi, 1 over sigma. So we can see that sigma is, we can also do this, right? So 1 over sigma will be phi to the power of half. So convince yourself this is right. So this is 1 over sigma, which will be phi square root of phi. Okay. All right, so that's good. And it's also pretty straightforward to do this one because you have 1 over 2 times 1 over sigma squared, so that becomes phi over 2. Okay. Good, so everything else stays the same. And we simply replace the standard deviation with the precision. Okay. And the one last step that I will do for you, which will complete the likelihood function, is expand the terms, the product term over here. So this term does not change with the index, right? So the whole thing will just raise to power of n, okay? Because you're producting n copies of them. Okay? So what you have is, and phi to the power of half raised to the power of n will be phi to the power of n over 2. Okay? And what's important now is in the exponent. So we know that if you product multiple exponential functions together, it's going to be a large exponential with all of the terms sum up together in it, right? So this is algebra. Make sure that you familiar. So we can actually come to the term that is going to be the sum in the exponent. And because phi doesn't change by the index, the only sum that we're summing over is over here. Make sense? Okay, so convince yourself that this is true. Okay? And before I go to the prior distribution part, something good to keep in mind, we're gonna come back to this again, of course. But something good to keep in mind is, like I said, we like to use, to recognize what is constant. And then because once we know those, we can throw them into the proportional sign so we don't have to worry about them in the derivation too much, okay? So my question for you now is, there are three terms. 1, 2, 3. Which are constant in terms of mu? The first one, constant, right? Second one, constant, right? Third one, because mu is here. So constant, constant, not constant. Okay? So soonish, when we are trying to derive the posterior, you will see that those two go away. We don't need them anymore. Okay? So good to keep in mind. I mean, of course, you still have to work with this part. It looks a little bit complicated, but we're going to look at the detail in a minute. Okay. All right, so this is the part about the likelihood function. So let me also introduce you to the prior. So the prior distribution, we know that is a normal. So I'm going to also use the precision instead of the standard deviation. So we know that the prior for mu is normal, mu 0 and sigma 0. Okay? So that's the setup that we had in the first place. Okay? And again, we put this in the conditional sign because it helps us to recognize that this is known and this is being conditioned. Okay? All right, so the prior distribution now is also a function of mu. So you notice we keep writing the functions in terms of the only unknown parameter, because later we're going to use them to derive the posterior. So I'm going to write the density for you. So now is sigma 0, and then the exponent. This is just the regular normal density, okay? But you need to make sure that you get the correct mean and standard deviation. So previously, mu itself is the mean, and sigma itself is the standard deviation for the likelihood. Okay? Now, it's a prior distribution for the unknown mu, and we put a normal prior for it with mean mu 0 and sigma 0. So that's why the density PDF of mu itself is in terms of sigma 0, mu 0, and it's unknown. Okay? So this definitely needs practice. I mean, it's easy. I mean, it looks easy when people show you this, but then when you try to derive it later, it might be pretty demanding. So I'm trying to highlight the key steps. So again, we define the precision. I'm going to use P0, which is 1 over sigma 0 squared. Okay. So I'm going to use that for the later derivation. So that simply means I have sigma 0, 1/2, and in the exponent, Make sense? Yeah, so what we did is we just replaced the standard deviation with the precision. So before we move on, go practice 3 terms, which are constants.
First two.
First 2 again, right? Constant, constant. The third one is not a constant because mu is involved. Yeah. So later, when you're writing the posterior, you see that this 2 is going to go away. But then, of course, as you can see already, that the third term, not only here in the prior distribution, but also in the likelihood, is kind of involved what mu is, right? Especially previously, it's the summation of a bunch of square terms. So there's some practice and good, I would say, techniques over there that is worth going over, and we're going to turn to it now. All right, so posterior. All right, so posterior, remember, I usually write in the conditional probability or conditional distribution format. So here is a mu given all of the data and sigma. Okay, it's good practice to keep the sigma there. So we know you should be proportional to the product of the prior and the likelihood. So I'm going to write some terms for you, and I give you some time to try to derive it. And from the prior, remember only the third term is not a constant, so only that term matters, right? And I will also write it for you that, I should say, I think it's this over phi and then sum of all of the yi minus mu squared, right? I think that's what the posterior, no, the likelihood part that is not a constant. Okay? So this is collecting what we have previously. So before I break to let you try it, I should just do one more thing for you. Because later, remember previously when I show you what the posterior is, there's no more yi, it was expressed in terms of y bar. Okay? So that's actually a pretty standard practice when you're doing this kind of derivation for the normal conjugate prior practice. So it's good to, so let me show you, it's good to recognize that, okay, so pretty much I'm trying to show you how to simplify this particular term, so later it's easier to see the results. So I'm only going to focus what's in the exponent for now. Okay? So what I will be doing is I will look at this part. The reason why I'm doing it here, as you can see soon, because even though those 2 exponential terms inside, it has mu in it, but you also say in the first term you have this mu 0, right? When you expand the square term, you're going to have a squared mu 0, which is a constant. Okay? So right now I'm trying to, or we all should be trying to get rid of any unnecessary constant in here, that in the end, we're only going to be left with terms about mu. Because those are going to help us to determine what's the posterior distribution. Okay? So let's try to simplify this a little bit more, so we only need to worry about the mu term. So we can all do this. I mean, this is standard exercise. So I will stop talking and do my part here, and you can try yours. I think this is good enough. Does this make sense? Yeah, so I expect the sum of the square term in the exponent. I mean, yeah, only the part like without the negative p over 2 for now. And we can get the sum of y squared minus 2 times n times y bar times mu plus n times mu squared. Okay, so the first term, it's about the data. It's nothing about the mu, right? So later, as you can see, that can go into the constant. So that's why right now on the right top-ish, when in the green color, I further simplify that to be proportional to the exponent of negative p over 2, and only keeping n mu squared minus 2n y bar mu. So we're going to use this later when we derive it. Okay. So the green part in the bottom is trying to give you, it's a shortcut, it's a demonstration of how to further simplify it only in terms of mu squared and mu. Okay. All right, so I'm going to erase this part, and then I will give you a few minutes to complete the square. So what I mean by complete the square is now, I mean, there is still some work you can do with the first exponent from the prior, right? Because it's negative p 0 over 2 times mu minus mu 0 squared. So if you expand that square term, you will get mu squared, right? Negative 2 mu 0 plus mu 0 squared. So mu 0 squared should go away. going to the proportional sign because it's a constant. Okay. So try to do that. I will stop talking for a little bit. Try to do that, and you will start to recognize that for both exponent terms, you have something about mu squared, you have something about mu. Okay. If you combine those terms, you might be able to recognize what the distribution is. Okay. So I'm going to pause for a few minutes. Take your time. This is, especially the first time seeing this will be a little bit stretching of your skills and practice. So take your time, and we're not in a hurry to rush in any case. So the goal again is try to only have the terms about mu squared and mu. Okay. So from there, you might be able to see something. I know some of you are working. I should just give one more thing. Because once you arrive at some point, what I mean by complete the square is to see what the distribution is. So generically, we know that if you have ax squared plus bx plus some constant, you're able to complete the square. Right? So what this, so I would do this, I haven't done this for a while, so this is what the for ax plus a constant, right? And that gives you x plus, I think it's b over 2a, right? Squared, right? And then the still plus the constant, the c, but you have to minus, right? So this is the standard practice by completing a square. So I'm mentioning this because, as you know, the density of the normal is what in the exponent? If y follows normal, mu sigma, then density of y right? So mentioning the completing the square practice is because once you have done the further, I would say, trying to simplify, further simplification of these two terms, and we know it's two exponent terms multiplied together, right? So it can be combined into one with the sum of the inner parts. So once you do that, you will have some terms of mu squared and have some term of mu. And if you complete the square, you might be able to recognize what the new mean should be, because that will be a posterior mean. Because I already said the posterior is a normal distribution, right? So now we have most of the terms there. The goal is to make sure that you can recognize, after simplification, you can recognize what will be the mu in the posterior, and of course, the sigma squared in the posterior. I already showed you the results, but I bet you don't remember it anyway unless you wrote it down because it's complicated. But if you keep doing this, we're going to pause for a few more minutes. But I want to mention what I mean by complete the square. And the generic form is this. And the goal is to help us to recognize this. So of course, in the normal term, it's going to be a negative sign over here. And then you'll be able to recognize this b over 2a is the mean. Okay. And whatever is multiplied beforehand will be related to the standard deviation. Okay. So take your time, and I'm going to pause for a little more. Just want to share with the hint so you know what to expect. Like which is like it's like really calculated. 1 over 2 pi sigma exponent.
Looking from you.
Yes, yeah, basically. And we know
Why not?
Yeah. That's one here. Yeah.
and so I wrote the next step, which is what you, if you get it correct, I mean, if you do it in the right way, you should get to this point. So this is further simplification and combine the terms of mu sigma, mu square and mu. So in front of mu square, it's negative 1 over 2 times p0 plus n times p. And in front of, I think I have one more. Yep. And in front of mu, it is 1 over 2 mu 0 phi 0 plus 2 times n y bar times b. And then the last step, I mean the next step I should say, is complete the square. So I'm going to show you the results here. I think I missed a 2 here, sorry. There should be a 2 here. So I will share notes afterwards, of course, so don't worry too much, but I do want you to try to do it in class, and this is definitely important skills in the normal case. So this is after you complete the square, this is what you get. And just like what I wrote earlier, if you look at the normal density, you can start to recognize what is the mean, posterior mean, and what's the posterior standard deviation, right? So posterior mean is whatever in the square term that is being subtracted from unknown mu, right? So posterior mean is this guy. It's going to be mu n. And this part, remember, if we express the normal PDF in terms of precision, this is exactly what is being multiplied before the square term, right? So this should be what?
1 over square root.
Yeah, or if you, yeah, so for the precision, the posterior precision will be this, and then the posterior standard deviation will be 1 over this and then square root, right? So ultimately, we have the posterior be normal. So the mean is what we have over here is mu n. So it's phi0 mu 0 plus ny bar phi divided by phi0 plus np, right? And then the standard deviation is 1 over phi0 plus np. And that's what I showed you earlier on the slide. Yeah, so the details, obviously, you might want to go back to work out, but ultimately, the key skill over here, I think it's making sure that you get the right terms, recognize what is constant, be able to throw it away into the proportional sign, and then, of course, in the end, complete the square. Okay? And the reason why we complete the square is because our goal is trying to recognize what is the density for this. And as you can see, we again are using all of this proportional sign, right? So for this case, we won't go into the detail of keeping those constant and trying to show that it is indeed a normal density. That's too much work, but just please make sure that you are able to follow what we showed in class today using the proportional sign, and be convinced that in the end you do come to a normal density in this way. Okay? So I will share notes afterwards, so don't worry. So I'm going to clean this now and bring back to the slide that we have here. So this is exactly the equation 14 that was the derivation exercise that we did. So we have a few more minutes left. The only thing I want to talk about is just looking at, sorry, I have to close this down. Looking at the posterior mean for a second. So in the beta binomial case, I show you that the posterior mean is a weighted average of the prior mean and the sample mean, right? So I want you to do the same practice here. So obviously, prior mean is this, right? Sample mean, you can think of it as it's y bar, but you can also think about it as, sample sum in some sense, because that's all the contribution together. Right? So you can see that in the numerator is phi0 times the prior mean plus phi times the sample mean or the data mean, right? No, I think it's easier to just recognize the sample mean. Sorry about that. So just focus on the sample mean. So this is the weight, part of the weight, right? And I should say these are the part of the weight, n times phi. And as you can see in the denominator, is the sum of these two. So what are the weights? The weights for mu0 is phi0 over phi0 plus np, right? And the weight for y bar is np over phi0 plus np. Okay. So again, the posterior mean is a weighted average of the prior mean and the sample mean. And then, of course, how large is phi0, how large is phi, and how large is the sample size going to play an important role in terms of how much of contribution to the posterior mean is from the prior mean and from the sample mean. And n, which is the sample size, obviously, as n grows bigger, contribution of y bar is bigger. And this also reinforces our idea that if you have a larger sample or have larger amount of data, the data are going to start to dominate the posterior. Okay, so this again, as you can see, I mean, this is the same sort of like similar approach, a story to think about the whole structure that at the beginning we talked about how the prior and the data contributes to posterior. And then in specific model, like beta binomial, and here we call this normal model, because the normal density and then you put a normal conjugate prior. So we call it normal. And in this case, in those two cases, you can see exactly how, say, like the prior sample size, the data sample size, etc., all of those are contributing to the posterior in the way that we think they should. Okay? And, okay, so we're going to end here today. So on Thursday, make sure that you bring homework 2 and lab 1. And make sure to complete your data camp courses. One is due today, at night in the evening, and the other one is due for 1 week from today. On Thursday, we're going to do lab. So I still have some slides to finish. And on Thursday, we're going to do that. And then we're going to work on lab. You can work together, and then I'll provide you some questions so you can practice your R program. Okay? That's it.